is going to talk about recently added features in DCDFTBMD program. Please.
Microphone is okay?
Yes.
Okay. So first, I'd like to thank the organizer for giving me an opportunity to give this presentation on behalf of the Professor Nakai. The title of my talk is Recently Added Features in the DCDFTBMD program. DCDFTBMD is a linear scaling semi-empirical code developed in a Professor Nakai group. It can perform large-scale quantum chemical calculations based on the divide and conquer density functional tight binding method. Molecular dynamics and free energy calculation by metadynamics, geometry optimization, and other simulation methods are supported. 2 years ago, Professor Nakai introduced this DCDFTB code in this conference. The motivation was to develop large-scale chemical reaction simulation method, especially filling the gap between quantum mechanical-based techniques whose system size is typically limited to hundreds to thousands of atoms, and classical approaches that can treat very huge systems like the protein structures. But these classical MD techniques are non-reactive, unfortunately. So in his last presentation, the theoretical background of the DCDFTB method was explained. In short, divide and conquer is one of the fragmentation-based computational techniques for reducing the computational cost and for achieving the linear scaling with respect to system size. The entire system is divided into the so-called subsystem without mutual overlap. For example, shown as this red square region in the case of Fourier molecules, and each subsystem is augmented with the buffer region, shown as the orange square region, to mitigate the accuracy deterioration due to the fragmentations. And DFTB is an approximate version of the density functional theory, and in this slide, only the total energy expression for the ground state is shown, which is obtained by Taylor series expansion of the DFT total energy and classified into different computational models, DFTB 1, 2, or 3, depending on the expansion orders. So DFTB can satisfy good balance between accuracy and efficiency by adapting the appropriate DFTB parameters to the specific systems. The efficient implementation of the DCDFTB method on massively parallel computers was also discussed in Professor Nakai's last presentations. Briefly, the subsystems which was introduced in the previous slide are assigned to computer nodes or MPI processes, and the remaining procedures are parallelized with the OpenMP multithreadings. And our benchmark test on the K computer, which was the predecessor of the Japanese flagship supercomputer, confirms that this developed hybrid algorithms show the good performance for this kind of isolated cubic water box containing up to 1.5 million atoms. And we have applied the DCDFTBMD code to solution, battery, electrolyte, biomolecules, and solid surface systems. And this graph shows the accessible system size and the simulation time by massively parallelized DCDFTB method. And several examples were already presented by Professor Nakai. The largest case was to unveil the proton transfer mechanism of bacterial rhodopsin embedded in a lipid membrane with water, where approximately 50,000 atoms were fully treated quantum mechanically. And herein, I'd like to introduce the recent advance of the DCDFTBMD code after the NIS 2020. The contents is listed in this slide. And first topic is about the improving the system size limit, beyond the 1 million atoms by using the current Fugaku supercomputer in Japan. The Fugaku supercomputer is a Japanese flagship high-performance computing system in operation since 2020. And it was ranked as the fastest supercomputer in the top 500 in 2020 and 2021. And compared with the predecessor of the K computer, the total number of nodes was almost doubled, and the number of cores was increased by more than 10 times. And to use such kind of great computation resources as efficient as possible, we evaluated and improved the code in these studies. And The target was to set to perform the full quantum chemical calculation for more than tens of millions of atoms at the DC-DFTB levels, not only for the isolated systems, but also for the periodic systems as well. To accelerate the DC-DFTB calculation for periodic systems, we adopted two efficient algorithms for charge-charge interaction evaluations in the two electron integrals in Hartree-Fokker DFT calculations. First, for the first term of gamma function that describes the long-range Coulomb interactions, the originally employed Ever's summation was replaced to multifold-based algorithms to speed up the calculations. Second, for the second term of this kind of gamma function that involves a large number of division and exponential operations, the cubic spline interpolation was used instead of the direct computation to increase the efficiency and considering its short-range natures. And these two algorithms can be implemented incompatible with the massively parallel algorithms presented in the previous slide. And we numerically checked the accuracy and efficiency of the developed algorithm, which is termed multiple spline in this slide. The left figure shows the time cost changes of the total energy in microcanonical ensemble for cubic water box containing 500 water molecules. And with the choice of appropriate parameters, such as the multifold expansion order and the grid size of cubic spline interpolation, the developed multifold spline algorithm can reproduce the trajectory obtained from rigorous evaluation of charge interaction functions by Ever's summation and direct computations. The right figure shows the system size dependence of elapsed time of one MD step on a single node workstations. The scaling of conventional DFTB is close to cubic, which is due to the matrix diagonalization path is a bottleneck of the calculation. And this bottleneck was removed by the divide and conquer method, and the scaling was improved to order 1.6. And then the present algorithm further reduced the computational cost, and quasi-linear scaling of order 1.1 was achieved. The efficiency of the developed algorithms was tested on now the supercomputers. The system size dependence of the elapsed times or measured on the predecessor of the K computer and the current supercomputer Fugaku was measured and shown in a double logarithmic plot. The obtained results indicated that the massively parallel DCDFTB and periodic boundary condition calculations are greatly benefited from the increased arithmetic performance obtained by switching from K to Fugaku supercomputers. The reasonably fast quantum mechanical molecular dynamic simulation for the millions of atoms, the largest case was about 3 to 4 million atoms in this case, could be performed in several seconds per MD steps. So it seems that the very fast quantum mechanical molecular dynamics simulations is possible by using the DCDFTB MD code. But it was difficult to treat even larger systems due to the large memory requirements. To enhance the memory saving, we recently developed the direct SCC algorithms. In these algorithms, similar to the direct SCF that recalculates the necessary integrals in each FCF iterations, the necessary charge-charge interaction functions are calculated on the fly in each SCC iterations. Moreover, charge-independent Hamiltonian denoted as H0 in this slide is added to the quantity to be recalculated in order to further reduce the memory requirements. We noticed that this modification does not increase the overhead significantly as the DFTB method relies on the table lookup for this kind of charge-independent Hamiltonian calculations. The efficiency of the direct HCC algorithms was assessed using the cubic water box consisting of about 5 million atoms using the supercomputer Fugaku. These bar graphs show the elapsed times for the energy and graduate calculations. That shows the total computational times using a different number of cores. And the total elapsed times of one MD step confirms that a satisfactory scalability for this kind of direct SCC calculation with DC-DFTB levels. And also considering the elapsed time on the order of minutes, the present approach seems to be feasible for treating more than millions of atoms at the DC-DFTB levels. The system size limit of the direct SCC-based DCDFTB calculation was investigated on the supercomputer Fugaku. The three parallelization patterns were tested, bearing the maximum memory size per MPI processes, 8 or 16 or 32 gigabytes per MPI processes. The developed algorithms enabled single-point energy calculation for cubic water systems containing more than tens of millions of atoms. And the finally achieved system size for the energy calculation was 54 million atoms, which took approximately a few hours on using the roughly 6,000 nodes of the supercomputer Fugaku, which corresponded to the only 4% of the full capacity of the full resource of the Fugaku. The same assessment was performed for the non-self-consistent version of the DCDFTB, and the accessible system size was increased from the case of the SCC because some working arrays used during the SCC iteration were unnecessary. The largest system size for energy calculation reached to more than 1 million atoms, and this NCC procedure completed in a minute. And we believe that this kind of DCDFTB calculation for huge system is potentially promising to perform the rapid electronic structure for on the exascale supercomputers. And the second topic is about the implementation of the nanoreactor MD method and its extensions. In a previous topic, we could partially improve the system size limit, but the issue of running long simulation times remains. So the motivation was to accelerate the sampling of reactive events involving a large number of atoms and/or molecules. The nanoreactor MD method was pioneered by Martinez and co-workers in 2014. And this technique employs the spherical boundary potential for confining the reactive molecules in finite system. And the sphere radius and possibly force constants are treated as time-dependent parameters for mimicking the effect of coupling with the pistons. The periodically pushing the molecule to the center of the boundary potential naturally increases the frequency and strength of the molecular collision, leading to the enhanced reactivities. So for easier understanding, I prepared the movies on acetylene polymerization reactions. The movie in the left panel was performed with a fixed boundary potential, namely the no compression of the nanoreactors. In that case, the reactive events were scarcely occurred for the first tenth of picoseconds. And the right panel was performed using the nanoreactor method. In this case, we can see a number of reactions by the C2 species in the nanoreactor, resulting in a rapid growth of carbon-containing fragments shown in these movies. The time series of the molecular size distribution was plotted, where we confirmed that the nanoreactor certainly accelerated the formation of graphene-like structure and completed participation of all reactants on the order of hundreds of picoseconds. As demonstrated, nanoreactor MD method has been applied to complicated processes occurring under extreme conditions, while the application to condensed phase systems was little explored. Towards the efficient sampling of multi-component processes under relatively mild conditions, we modified the algorithms to control the target of the nanoreactors. In the present approach termed the species-selective algorithms, the inactive chemical species are predefined in advance, and they move freely inside the outer boundary potentials in this black side potentials. On the other hand, the reactive species are still accelerated by the nanoreactors. The implementation is robust for thermal vibration of molecules and isomer identifications by introducing the chemical species recognition step during the MD simulations. The species-selective nanoreactor MD simulation was tested for nucleation of the sodium chloride in saturated aqueous solutions. This kind of salt crystallization process has been investigated at the classical molecular dynamics level by sampling hundreds of nanoseconds to microseconds, which was quite difficult by using the quantum mechanical MD approaches. And here, as shown in the initial and final snapshots, where the production run was performed for the 4 nanosecond samplings, if we didn't use species selective nanoreactor methods, this kind of disordered structure was obtained. While by using the species selective nanoreactor method, this kind of ionic core-like species were obtained. And this figure shows the time course changes the gyration radius, indicating the compactness of the systems. And from this graph, clearly we can confirm that in the species of selective nanoreactors, large compactness was obtained for the sodium chloride, while the size of the water droplet was retained during the nanoreactor dynamics simulations. And as a check of the structural properties, the radial distribution functions are plotted in this slide. The critical difference between the without and with the species selective nanoreactor is the appearance of first peak for the sodium chloride pair and the decreased peak height for the sodium and oxygen pairs. And these results highlight that promoted sodium chloride ion pair formation and the distribution of water solvents from the sodium cation species, and leading to the acceleration of the ion association event and complementing the original nanoreactor MD method. And finally, we mentioned the progress on the integration of DCDFTB with MD with external softwares. And we have so far developed the interface of the file-based communication for enabling external calculation in Gaussian, ASE, QB, and PIMD, which may open the possibility of QMM treatment and other advanced DCDFTB-based molecular simulations in the future. And also, the socket-based communication was recently added for interfacing DCDFTBMD with IPy, a Python program with the strengths on path integral molecular dynamics simulations. And such a combination was further considered to describe the new quantum effects in the large-scale quantum-based simulations termed DCDFTB-PIMD. For practical quantum mechanical path integral molecular dynamics simulations of thousands of atoms, this kind of client-server scheme was adopted. In this framework, IPy distributes the bits, which are the representation of the quantum particles with several classical particles connected by strings, and the calculation of each bit is parallelized with the DCDFTB-MD code. And the efficiency of this IPy DCDFTB-MD framework was examined. The left panel shows the elapsed time for the 400 MD step of a cubic water system containing the 216 water molecules. The reasonable speed up by increasing the number of cores was observed for up to the 32 bits. The right panel shows the relative speed up of benchmark calculation, reaching to the parallel performance as high as 87%. So this kind of framework is applicable to the supercomputer or similar high parallel computer resources. We tested the large-scale DCDFTB PIMD simulation for bulk water containing 500 molecules, so more than 1,000 atoms. The beta agreement with experimental data was obtained for radial distribution functions of OH and HH pairs as shown in this figure. Meanwhile, both MD and PIMD described well after the second peaks for these pairs. Consequently, the nuclear quantum effects contribute to intramolecular structure, yet the effect is rather small to the radial direction of the hydrogen bond structures. We also calculated the tetrahedral order parameter as an indicator of hydrogen bond network in bulk waters. The horizontal axis of this graph is defined with this equation, where values of 0 and 1 correspond to the random arrangement and perfect tetrahedral network, respectively. The distribution plot indicated that the nuclear quantum effects enhanced the tetrahedral hydrogen bond structures. And these results demonstrate that the advanced DCDFTB simulations can be performed by the unification with the external softwares. And finally, let me conclude this presentation. This talk summarizes the recently added features in the DCDFTB-MD programs, the progress of utilizing modern peta to exascale supercomputers, treating larger system sizes more than the millions of atoms, sampling by modified nanoreactor technique and integration with the external software hopefully enlarges the capability of the large-scale quantum-based simulations. And there finally, let me acknowledge the group members and the financial and computation resources shown in this slide. So that's all for my presentation. Thank you very much for your kind attention.
Explain me the IPI.
IPI is written in Python code, and which is a kind of molecular dynamics engine. Not only for the path integral MD techniques, but also they have the ring polymer molecular dynamics or central molecular dynamics, as well as replica exchange molecular dynamics simulation. Yes.
Just having this program, you have a chance of studying the conversions that size. How far if your program allows you to study already the converged systems, size of the solvent or still not?
I have not investigated such kind of direction, but I think I think it's not reached to the convergence, I think. At the moment, I think. Maybe more than maybe we need 1 billion atoms, I guess, but not sure. Yeah, thank you. Yeah.
Last thing,